This is an instructional video for the laboratory exercise called the simple pendulum. This is a laboratory exercise that you can conduct at home. If you are enrolled in Physics AB and in Honors Physics AB, you would do this laboratory exercise as a mini lab exercise on the handouts that are provided. If you are in AP Physics C, this is a formal laboratory report that is worth 35 points. Okay, the purpose of this laboratory exercise is to verify the following expression. We're going to verify that the angular frequency of the simple pendulum is the square root of G over L. This is the natural frequency of the simple pendulum. Okay, now in order to do so, there's a little bit of theory behind the exercise. Once again, for those of you that are enrolled in AP Physics C, when you conduct a formal laboratory report, you have to show this theory. Okay, now what we cannot easily measure with a stopwatch, for example, is the angular frequency. So then therefore we're going to write the expression instead in terms of the period. So the period is 2 pi divided by omega. Plug in the value of omega here into the denominator of the expression, and you end up then with the following expression, 2 pi multiplied by the square root of L over G. Okay, as is always the case, we're going to linearize our data, so then therefore I'm going to square both sides of the expression. That is like so. Okay, and then here is essentially the idea behind the experiment. What we will do for simple pendulums of various length L is that you'll measure the period with a stopwatch on your smartphone. We'll eventually then graph the period squared as a function of the length L. The slope of the line is going to be the quantity 4 pi squared over G. So then therefore we'll be able to use the slope to measure what G is equal to by arriving at a low percent error where of course G is 9.8 meters per second squared. We will then satisfy the purpose of the experiment. Okay, the experiment itself is conducted in much the same manner as the conical pendulum laboratory exercise from the first semester. Let me now take you through the procedure. Okay, first of all, you have to construct a pendulum. I suggest using a small weight to do so that you can tie some string to, for example, using a washer. Okay, and then the distance L. The distance L is always going to be from the geometrical center of the object, in this case the center of my washer, to where I'm pinching the string with my fingers like so. So construct your pendulum. I'm using a washer to do so. Okay, let's say that right here is where my finger is pinching the string. Okay, right here is the geometrical center of the pendulum. That's its center of mass. And then therefore right here, this is the distance L. What I want you to do is start with a distance L equal to 0.2 meters. And then using a stopwatch on your smartphone, you are then to time how long it takes for 5 oscillations. So then therefore I would, for example, hold it, say like so. I would then release it and set it into oscillation, and when I do, I would start my clock. And then I would count the oscillations carefully. So for example, I would say, okay, go. 1, 2, 3, 4, stop. Like so for a total of 5 oscillations. Make sure to count 5 oscillations and not accidentally 4 or 6. So we're going to call that time small t. So measure the time small t for 5 oscillations, and then from there big T, the period is equal to that time divided by 5. Okay, once you've done so for your first trial, then go ahead and start to construct the following data table. Okay, so your data table is going to have the following columns. You're going to have, first of all, L in terms of meters, 0.2 meters, 0.4, 0.6, 0.8, and 1.0. Okay, and then here is small t, the time in terms of seconds, big T, the period, the time in terms of seconds, and then when we get to the graph in just a few moments, what you have to do is calculate the period squared. When you gather your data, by the way, you may actually want to start down here at the bottom of the table with a 1 meter length pendulum, and then just cut it like so as you work your way up in this direction. That's perfectly fine. Okay, once you have this data table, then you construct the following graph. Once again, let me do some erasing here. Okay, so you then graph the period squared as a function of the length L in terms of meters. Ultimately, you'll draw a best fit line through your points. Okay, and then you calculate the slope. Now I'm going to call the slope here m. And then in theory, your slope should be equal to the following quantity. You set your slope m equal to 4 pi squared over what we'll now call g experimental. Go ahead and then solve for g experimental. It's equal to 4 pi squared divided by your slope. Of course, in theory, it should be equal to 9.8 meters per second squared. The last step is just to calculate a percent error. So the percent error is going to be the absolute value of the difference between g and g experimental. Divide that by g, and then multiply by 100, of course, in order to convert it into a percentage. If you count the oscillations carefully, if you measure the distance L carefully, then you should get really good results. Using a simple pendulum is perhaps the easiest and quickest way of accurately measuring G.